Hello guys, and welcome to the design of pad footing. So here you can see the figure of the pad footing here. It is the pad footing, and you can see the main reinforcement and distribution reinforcement of the footing. We will design this pad footing. Here you can see the reinforcement of the column coming from the top, and it will lie on the top reinforcement of the pad footing like this. And this vertical reinforcement or main reinforcement of the column will be supported, or it will be tied using the stirrups which are shown over here. We have already seen the design of the column, so now we will move on to the design of pad footing. There are various kinds of footing. In this video we will see the design of pad footing in various types of footing, such as isolated sloped footing as well as combined footing is also uploaded. So first we will see the pad footing. So here the question is provided like, design a isolated pad footing which is uniform thickness for an axial loaded column of 450 by 300 size. So here the column size is provided, and the soil bearing capacity is 200 kilonewton per meter square. The load coming from the column is 1000 kilonewton. Use 20 M20 grade of concrete and Fe415 grade of steel. So the given data is we have to design the isolated pad footing. Then the size of column is provided as 450 by 300 Then the SBC of soil is 200 kilonewton per meter square, and the load coming from the column is 1000 kilonewton. The grade of concrete is M20 and the grade of steel is Fe415. So here you can see the figure at the right hand side, which shows the footing in the blue color. This is the footing and this is the column. So we have to design this part, footing part. So we'll see this design of the footing. So let us start. So first step for the design will be, first we have to find the dimension, which means length and width of the footing. So for length and width of the footing, there are we need to do four things. So first we will do what we will do. First we will find the area of footing. So here what is the area of footing? So area of footing is equals to force upon SBC, which means soil bearing capacity. So in our case, the force which is coming from the column is 1000 kilonewton, plus we will add 10% as a self weight. So we have to consider self weight as for the area of footing. So what we will do? So 1000 plus 10% of 1000 divided by SBC, which is 200 kilonewton per meter square. So we will have the area of footing as 5.5 meter square. So next what we will do? We will provide the rectangular footing. So for rectangular footing, we know the dimensions A and B, which is the dimension of the column, and we have to find the B and L, capital B and L, which is the dimension of the footing. So let us start. We will use this equation as small a by b is equals to capital B by L. We know the value of small a and small b. We will make this subjective. We will make this subjective to the capital B, and so the value of so the capital B is equals to capital L into bracket small a by b. So we will have the value of small b, we will have the value of capital B, which means the width of the footing as 0.666 L. So we will have the value obtained as 0.666 capital L. So third, what we will do? We will use the formula of the area, and we will place the value of width of footing in this equation, and we will find length and width of the column. Length and width of the footing. So what we will do? We will use the area is equals to length into width. So we already have the area over here as 5.5 meter square is equals to, we don't have the value of L, we already have the value of B, which is obtained over here, which is 0.666 L. So we will place over here, and we will make this subjective to the L. So we have the length of footing as 0.87 meter and the width as 1.91 meter. So to make the area exact as 5.5 meter, we will adjust the length and width of the footing. So I have adjust the length and width of footing, and I have make the length of this footing as 2.75 and the width as 2 meters. So now what we do, we will fourth will verify the area. So fourth we will do is area required. So area required is equals to L into B. So this L into B will be the values which we have obtained from the number 3. So what the L is equals to 2.75 into B as 2. So we have the area as 5.5 meter square. So next, so here in this we have found the L and B as 2 meter and length as 2.75 meter, and we already have the value of A and B over here. So now as per IS 456-2000 clause number 34.1.2, the minimum thickness, the minimum thickness of the footing in soil should be 150 mm, and minimum thickness of the footing in the pile should be 300 mm. So in our case it will be the minimum thickness should be 150 mm. So let us now move on to the step number 2, which is thickness of footing. So first what we will do, we will find the ultimate load, which is PU. So PU is equals to factor of safety 1.5 into load, which is 1000, divided by area provided, which means the area which we have provided is in the first step is 5.5 meter square. So in this we do not have to consider the self weight as a 10%. So the value of PU, which means ultimate load, is 272.72 kilonewton per meter. So next what we have to do, we have to find three things. First we will find bending moment, second we will find two-way shear, and third we will find the one-way shear for calculating the thickness. So let us start with the first, the bending moment. So for bending moment we have to assume 1 meter strip. So I have assumed 1 meter strip. So first we will find the mu. So moment, so what the equation for moment is WL square by 2 into 1 meter, which means 1 meter as for strip. Per meter we will find for the per meter of the strip. So in our case we have the value of the WU, which means load, which is PU. So 272.72 kilonewton per meter. We have the this PU we can say. So what we have to do, we have to make the bending moment at the face of the column. So here you can see the brown thing. So we have to take this much part for the calculation of bending moment. So here this portion is given. I have cut it and placed over here. The H portion you can see, this is the face of the column. So and here is the load. So the load is 272.72 kilonewton per meter square, and the length distance is 1.15. So this distance came from, we already have the total distance as 2.75 meter. So 2.75 meter minus 450 divided by 2. So we'll have the value of this. So I have obtained the value as 1.15 meter. So in our case the moment will be load into distance square by 2. So load is 272.72 into 1.15 its whole square divided by 2. So in our case the moment is 180.34 kilonewton into meter. So next what we will do is we will do mu is equals to RBD square to find the depth, which means to find the thickness. So in our case the mu is already we have calculated over here. So mu is 180.34 kilonewton into meter. So we'll convert into Newton into mm. So we'll multiply this value with the 10⁶. So is equals to R, the value of R is 0.138 into FCK, which is 20, into the B. So the value of B is, we have assumed as 1 meter, so in mm it will be 1000 mm into D square. So we have to make the subjective to the D. So we will have the value of D as 255.62 mm as a depth of the footing, which is more than 150 mm as per the IS code, which we have seen in the further slide. So it is okay. So it is safe against bending moment. It will not fail due to bending moment. So second we will find with the two-way shear. So let us move to this two-way shear. So for two-way shear what we will do, so for two-way shear, first you can see this figure. The two-way shear will act at a distance of d by 2 from the face of the column. So here the hatching red hatch part is the effect of two-way shear, which will be act at a distance of d by 2 from the face of the column. So what we will do, so here we know this is the distance d by 2, here it is the distance d by 2, and over here also it is d by 2, so the distance will be 450 plus d. Similarly here it will be obtained as 300 plus d. So we will find the first VU. So VU is equals to PU into area. So the area, this area will be, we will see this area. So in our case PU is 272.72, then into we will see the area. So in our case area is, first we will see the area of the footing. So in our case area of footing is 2 into 2.75, which is the area of footing. So we have done 2 into 2.75. We have completed first area. Then second, what we will do, we will minus that area, and we will, from that whole area we will minus this area, this much area we have to deduct. So minus PU, which is 272.72, into 0.3 plus d, which is this value, into 0.45 plus d. So we will have the value of VU as in this term of the, as in the equation form. So we have to place this value of VU as in this form only. Now next we will move on to the tau V. So we will move on to the tau V. So tau V is equals to VU upon BD. So we know tau V is less than or equals to tau C. So we'll make the value of tau C as 0.25 under root FCK. So it has 1.1 MPa, which is 1.11 Newton per mm. So we already found the value of tau V as 1.1 MPa. So we'll place the value of tau V as this, and value of VU as we will place this equation. So here we have placed this equation for the VU. So divide by B into D. So over here we will have the value of the D. So for the value of B we have the value as the 1.5 plus 4D. So it came from here, it is the parameter. So parameter will be 2 times 0.45 plus D plus 2 times 0.3 plus D. So we'll have the value of the B as 1.5 plus 4D. So after solving this, we will have the depth of the, or thickness of the footing is 710 mm, which is more than, we can say, which is more than 150, we can say more than 150 mm as per the IS code. So it is okay. So from this, from the first bending moment and from the second two-way shear, the maximum value of the depth is 710. So we will use the value of the or the thickness of footing as 710. So it is the effective depth. So we will find next, we will find the overall depth. So the overall depth is equals to effective depth plus clear cover. So we will assume the clear cover for the footing as the 40 mm. So we will have the overall depth as 750 mm. So next, third, we will check for the two-way shear. Well, it will be failed due to one-way shear or not. So for it we will do as, first we will find, here you can see the figure, the two-way shear will act, sorry, the one-way shear will act at this portion which has been hatched at the distance of D from the column, from the face of the column. So here it has been displayed. Here you can see the face of the column which has been hedged, and this is the D distance from the face of the column, and it is D, and the whole distance is 1.15. So we will have this distance as 1.15 minus D. So let us move on to the calculation. So VU is equals to PU into area. So we have PU as 272.72 into this distance we have as 1.15 minus D. This is the distance of that shear, one-way shear. So we have the value of VU in terms of the some equation, so will remain in this thing only. Next we will directly move on to the VU. So VU is equals to tau V upon BD. So we will place the value of VU as we have found it over here, so divide by B. So in our case B is 1, so because we are finding for the per meter, so we will place as the 1 into D. So we will have the we have already have the value of D, so we will place the value of D as the 710, which is effective depth, which you have been calculated in the previous slide. So it will be 710 as the effective depth of or effective thickness of the footing. So we'll have the value of VU as we will have the value of tau V as 0.169 MPa. So next we will find as tau C. So tau C is equals to 0.25 under root FCK. So we will have the value of tau C as 1.1 MPa. So in our case tau V is less than tau C, which is 0.196 is less than 1.11 MPa, which means okay, there will be no shear failure. So we have completed with the second step, and we have founded the effective depth of 710 and the overall depth as 750 mm. So let us move to this step number, it is in the continuation of step number 2. What we will do, so we have already found we have the value of mu as 180.34 km into meter from the step number 2. Point number 1 we have already calculated. So here we have found the value of the moment as 180.34 km into meter. So we will use over here. So here is the value of mu. So next we will find the mu upon BD square. This all things are done for the for finding the reinforcement. So first we will do is mu upon BD square. We have already have the value of moment, so we'll place the value of moment. Then we have the B. So B is into per meter, so we will have 1000 mm into D. We have effective depth as 710 and its whole square. So we have the value of mu upon BD square as 0.357. So we have to move on to the SP16 page number 48. From that we will see the ratio of mu upon BD square. So in our case we'll see the higher value. So in our case the higher value will be 0.4 and the grade of steel is Fe415. So we will have the percentage of steel as 0.114. So we have found the value of percentage of steel as 0.114. And so we will find the capital AST. So the capital AST is which means area of steel in tension, which means which can be calculated as PT BD by 100. So in our case PT is 0.114 into B, which is 1000, and D is 710 divided by 100. So we have the area of the steel as 809.4 mm square. So next we will find the numbers. So numbers equals to capital AST divided by small AST. So the capital AST is the 809.4 mm square divided by small AST is the area of the bar. So I have assumed the diameter of bar as 12 mm. So we'll have pi by 4 into 12 whole square. So I have found the 7.162 numbers per meter of the strip. So we'll find the spacing. So spacing is equals to 1000 divided by 7.162. So it is 139. So I have made it round off, and it is 130 mm center to center, which is less than 300 mm center to center, which means okay. So I have provided 12 of 130 mm center to center as the main reinforcement. So next we will move on to the step number 3, which is the bearing check. So for the bearing check we will first find the bearing stress applied. So bearing stress applied is P by A. So in our case the P will be the ultimate load, which is 1.5 into 1000 kilonewton, but we will convert into newton, so it will be into 10⁻³ divided by area. So in this the area will be the area of the column. So the size of the column is 450 by 300. So we have the bearing stress applied as 11.11 MPa. which should be less than resisted. So let us find the resisted. So the bearing stress resisted is equals to 0.45 FCK into under root capital A1 by A2 or 2, whichever is minimum. The value of under root capital A1 upon capital A2 or 2 M2, between these two the minimum value should be taken and it should be multiplied with the 0.45 FCK. So let us first find the value for the capital A2. So the value of capital A2 is the area of the, we can say, area of the column, which is 450 into 300. So we have the value of area is 135,000 mm square. Second, we will find the area of A1. So for finding the area A1, so we will take the maximum of 1 or 2. So we have to take the maximum of these two. So let us see what is 1 and 2. So in this one, so the first is B into L, which is the we can say the size of the footing or the area of the footing, which is 2000 into 2750. So we'll have the area is 555 times 0 mm square. So the second we will do is B plus 4D into capital D plus 4D is equal, so we will have the value as 10330,600 mm square. So we will find the ratio. So we have found the ratio of A1 upon A2, under root A1 upon A2. So we will have the area so the ratio is 6.32. So 6.32 or 2. So in this 2 the minimum is value is 2. So we'll use the value as 2 and it will be multiplied with the 0.45 FCK. So we have the bearing stress resisted as 18 MPa. So it is less than 11 point, which is greater than 11.11 MPa. So it is okay. So let us move on to the fourth step, development length. So the equation for the development length is already provided in the IS 456-2000 page number 72, page number 42 and 43. Here the equation is provided as LD is equals to diameter of reinforcement sigma s upon 4 tau bd. So here the value of tau bd will be obtained from the table clause number 26.2.1.1 page number 43. So about that we have to see the grade of concrete. So in our case grade of concrete is M20, so the value of tau bd will be 1.2. so we'll use 1.2 as a tau bd. And the code also says that for deform bar we have to increase the 60% of this value. So we'll increase in 60% of the value. So let us see the solution. So in our case LD is equals to 0.87 4 into 415 into 12 divide by 4. Tau bd is 1.6 into, we will increase the tau bd is 1.2 and we will increase the value with the 60%, so we'll multiply by 1.6. so we have the development length as 564.14 mm, so which is less than this distance which we have calculated in the further slides is as 1.15 meter. So it is converted into the mm, so is 1150 mm. So we have to provide straight bar. If in case the value of development length was greater than, we can say 1150, so we have to bend this reinforcement as like this. But in our case we have to provide this straight reinforcement only. So fifth, we will see the minimum reinforcement and figure. So first we will find the minimum steel. We will use the 12% of area, so 0.12 divided by 100 into area, as we will use the area as the 1 meter strip into the thickness. It is the 1 meter of the strip into, we will see the depth, which is the overall depth, capital D we will use. So in our case 1 meter means the 1000 mm into overall depth is 750. So we'll have the minimum steel area as 900 mm square. So we will provide 12 dia 120 center to center. So here we have to plot one figure like this, which shows the length and width of the footing as well as the size of the column 450 by 300. So we will place the main reinforcement. So here is the main reinforcement over here, you can see, which is 12 of 130 center to center, and this is the minimum reinforcement, 12 of 120 center to center, and the thickness of this effective thickness is 710, and the overall is 750 mm. So here you can see the cross section. Here you can see the red reinforcement are the distribution reinforcement or the minimum steel, 12 of 120 center to center, and here you can see the main reinforcement which are in the green color, and you can see the brown color reinforcement vertically coming from the column will be rested on the top reinforcement of the footing, and this column reinforcement will be tied with the stirrups. So here we successfully complete the design of pad footing. Thanks for watching. Subscribe to my channel. Thank you.